our beautiful Mother Earth, our very own captivating, living and thriving home of hope. The only planet we know that holds life together. A planet that needs to be nurtured today with greater care than ever before. Melting glaciers, rising sea levels, extreme weather conditions, unusual floods and drought, increased frequency of hurricanes, cyclones and storms. Our fast-changing Earth now needs interventions by those who know her better than anyone else, the geoscientists. The call of the hour is to devise an emergency survival strategy for our planet. And what better place to do this but the Indian subcontinent? In South Asia, you will find unique and evolving geological wonders. South Asia spans the most spectacular ensemble of geological features and environments on the planet. The mighty Himalayas and Karakoram, the dynamic mountains rising ceaselessly, controlling the unique hemispheric scale monsoonal circulation, the cold arid deserts of Ladakh and Spiti in the north, the scorching hot deserts of the west, the Thar, the large river systems transferring sediments from mountains to plains to the oceans, the largest quaternary basin of the world, the enormous Indo-Gangetic plains, the vast stretch of mangrove, the Ganga-Brahmaputra Delta system, a UNESCO World Heritage Site, an active volcano at Barren Island, one of the most spectacular outpouring of continental flood basalts, the Deccan Traps, a celebrated example of extraterrestrial impact crater, the Lonar Lake, the illustrated signatures of Pangaea breakage, the Gondwana basins, a vast storehouse of fossils that records the evolution of life, preserved in the rocks cutting across geological time periods. Some of the world's oldest rock formations in our planet's geological history, the Peninsular Shield, extending into Sri Lanka, enticing deposits of iron, base metals, diamonds, bauxite, coal and petroleum, almost all known mineral classes. All this and more make the subcontinent a compelling destination for every geoscientist. IGC 2020 in South Asia will offer a large number of excursions in the Indian subcontinent. That will be a matchless opportunity to feel and appreciate the pristine signatures of the geological processes that have shaped the world, from the Archean times to the present. New Delhi. India's capital is well prepared to exceed all your expectations. The state-of-the-art India Expo Center, a modern, high-tech and world-class convention center, is waiting to bowl you over with its range of amenities and services. Delhi has a state-of-the-art international airport, ranked second best in the world by the Airports Council International. The airport connects all major global destinations directly. Delhi is well equipped to enchant every visitor with both budget and star-rated hotel accommodations. The subcontinent's legendary sense of hospitality is waiting to greet you, straight from the heart. India's capital city is right at the center of the world's favorite tourist destination, the Golden Triangle, an exciting space that assimilates the vibrant colors of Jaipur. with the historic monument to love, the Taj Mahal in Agra. Delhi opens up the windows to the incredible diversity of the subcontinent. The modern metro, with all its facilities, allows every visitor to savor its breathtaking variety of culture and fascinating range of cuisines. And we now hope to welcome them home with a smile.
Namaste to you, namaste to the world. This is Delhi for you. The city of joy, the city of fun. What you find here is stories and lore, the magic unfolds. Namaste to you, namaste to the world. This is Delhi for you. The city of joy where dreams come true.
Our beautiful Mother Earth, our very own captivating, living and thriving home of hope. The only planet we know that holds life together. A planet that needs to be nurtured today with greater care than ever before. Melting glaciers, rising sea levels, extreme weather conditions, unusual floods and drought. Increased frequency of hurricanes, cyclones and storm. Our fast-changing Earth now needs interventions by those who know her better than anyone else, the geoscientists. The call of the hour is to devise an emergency survival strategy for our planet. And what better place to do this but the Indian subcontinent? In South Asia, you will find unique and evolving geological wonders. South Asia spans the most spectacular ensemble of geological features and environments on the planet. The mighty Himalayas and Karakoram, the dynamic mountains rising ceaselessly, controlling the unique hemispheric scale monsoonal circulation. The cold, arid deserts of Ladakh and Spiti in the north. The scorching hot deserts of the west, the Thar. The large river systems transferring sediments from mountains to plains to the oceans. The largest quaternary basin of the world, the enormous Indo-Gangetic Plains. The vast stretch of mangrove, the Ganga-Brahmaputra Delta System, a UNESCO World Heritage Site. An active volcano at Barren Island, one of the most spectacular outpouring of continental flood basalts, the Deccan Traps. A celebrated example of extraterrestrial impact crater, the Lonar Lake. The illustrated signatures of Pangaea breakage, the Gondwana basins, a vast storehouse of fossils that records the evolution of life, preserved in the rocks cutting across geological time periods. Some of the world's oldest rock formations in our planet's geological history, the Peninsular Shield, extending into Sri Lanka. Enticing deposits of iron, base metals, diamonds, bauxite, coal and petroleum. Almost all known mineral classes. All this and more make the subcontinent a compelling destination for every geoscientist. IGC 2020 in South Asia will offer a large number of excursions in the Indian subcontinent. That will be a matchless opportunity to feel and appreciate the pristine signatures of the geological processes that have shaped the world, from the Archean times to the present. New Delhi. India's capital is well prepared to exceed all your expectations. The state-of-the-art India Expo Center, a modern, high-tech and world-class convention center, is waiting to bowl you over with its range of amenities and services. Delhi has a state-of-the-art international airport, ranked second best in the world by the Airports Council International. The airport connects all major global destinations directly. Delhi is well equipped to enchant every visitor with both budget and star-rated hotel accommodations. The subcontinent's legendary sense of hospitality is waiting to greet you, straight from the heart. India's capital city is right at the center of the world's favorite tourist destination, the Golden Triangle, an exciting space that assimilates the vibrant colors of Jaipur with the historic monument to love, the Taj Mahal in Agra. Delhi opens up the windows to the incredible diversity of the subcontinent. The modern metro, with all its facilities, allows every visitor to savor its breathtaking variety of culture and fascinating range of cuisines. And we now hope to welcome them home with a smile.
Namaste to you, namaste to the world. This is Delhi for you. The city of joy, the city of fun. What you find here is stories and lore, the magic unfolds. Namaste to you, namaste to the world. This is Delhi for you. The city of joy where dreams come true.
Okay, sir, we are live now.
Okay. All right. Hello, everybody. Good morning, good afternoon, and good night also for many people who are in Australia. So we have two talks now in this session. First is by Mike Searle, who is from Oxford University. And Mike has interest in tectonic evolution of the mountain belts, in particular processes associated with subduction, ophiolite formation, and abduction, folding and thrusting low-angle normal faults, for example, South Tibetan detachment, regional metamorphism, and crustal melting. He works mainly along the Alpine Himalayan belt, Karakoram range, and Tibetan Plateau region of South Asia, which is Burma, Thailand, Vietnam, Yunnan. He is interested in large-scale strike-slip faults, particularly Karakoram faults, Red Sea, and then the Dead Sea. His main interest up to now is on the Oman ophiolite and Oman mountains as such, where he is doing structural mapping, crustal shortening, balance and cross sections, PTT evolution, and subophilitic metamorphism, rocks of the subduction-related blue schist and eclogites, style of folding, thrusting, and similar things. And then obviously, he has worked on the eclogites from Oman, as well as he has done similar work in the Himalayas in Pakistan, India, Nepal, Sikkim, Bhutan, and he does regional mapping. He does in mapping regional mapping and structural study and combination of thermobarometry. So his main interest is leucogranite from Nanga Parbat, high pressure Soborari, as well as in the Pakistan, Khagan Valley. So like this, Mike has a very long list of interests, and he has been contributing. So I welcome Mike to make his presentation.
Okay, I'm going to talk about the geological processes of operating from what we can see from the geology of the Himalayas. And first of all, I would like to acknowledge with great sincerity the organizers of the HIGC in Delhi for doing a fantastic job. And it's just a huge shame that we can't meet in person in Delhi. Okay. So the title of my talk, Geological Processes and Timing of Subduction Initiation, Ophiolite Subduction, and Crustal Shortening and Metamorphism in the Himalayas. So some of the major questions we want to answer are, when did ophiolite abduction occur? When did the India-Asian plates collide? And when was the maximum crustal thickening occurring along the Indian plate Himalaya? Various models involve one end member as the critical taper model, and the other end member is the channel flow model. And finally, how does the Himalayan tectonics affect the thick crust of Tibet? Okay, so here's a picture of the Himalaya taken from the space shuttle as it's re-entering the Earth's orbit, somewhere roughly over Kathmandu, looking west towards along the arc of the Great Himalayas. It's a spectacular mountain range, and it's actually very simple. So all of these structures, the main central thrust, the South Tibet detachment, the Indus Suture zone, are all laterally continuous over a distance. And okay, I'm going to talk about the geological processes of operating from what we can see from the geology of the Himalayas. And first of all, I would like to acknowledge with great sincerity the organizers of the HIGC in Delhi for doing a fantastic job. And it's just a huge shame that we can't meet in person in Delhi. Okay, so the title of my talk, Geological Processes and Timing of Subduction Initiation, Ophiolite Subduction, and Crustal Shortening and Metamorphism in the Himalayas. So some of the major questions we want to answer are, when did ophiolite subduction occur? When did the India-Asian plates collide? And when was the maximum crustal thickening occurring along the Indian plate Himalaya? The various models involve one end member as the critical taper model, and the other end member is the channel flow model. And finally, how does the Himalayan tectonics affect the thick crust of Tibet? Okay, so here's a picture of the Himalaya taken from the space shuttle as it's re-entering the Earth's orbit, somewhere roughly over Kathmandu, looking west towards along the arc of the Great Himalayas. It's a spectacular mountain range, and it's actually very simple. So all of these structures, the main central thrust, the South Tibet detachment, the Indus Suture zone, are all laterally continuous over a distance of at least 2,000 kilometers. Two of the major processes operating there are, one is the lateral extrusion of the Tibetan Plateau on the left, which is this area of thick crust, 5 kilometers thick elevation, double continental crustal thickness, extruding to the east as a result of the Indian collision, bounded by these huge strike-slip faults, the Karakoram faults in the south-west and the Altintagan Kunlun faults along the north. The second major process is one of channel flow, which is the southwards extrusion of the metamorphic core of the Himalayas along the south. So here's a map of the Himalayas, I'm sure everyone is familiar with. And as I say, all of these zones are continuous pretty much along the whole length of the Himalayas. So it's a very simple orogenic cycle to deal with. So when you restore all the crust sheets of the Himalayas, what we're looking at is, again, a very simple passive continental margin of the northern margin of India. And here we have the Archean Indian shield in the south, and all of the major thrust sheets, the main boundary thrust, the main central thrust, the South Tibetan detachment, restored and preserved down to where they are cutting through the original stratigraphy of the Indian plate. And you'll see that in the lesser Himalayas to the south, it is almost entirely Proterozoic, and with some late Cenozoic molasse sediments on top. As you go into the high Himalayas, we're getting down into the high mantas, which are the Neo-Proterozoic, which stratigraphically overlie the Archean and the Paleoproterozoic of the Indian shield. And as you go towards the north, towards the continental margin, you're dealing with much thicker sedimentary package, which ends up with the Mesozoic sequences of the passive northern continental margin of India. And the one horizon that is common right across this entire mountain belt is the Neo-Proterozoic. It's present on the Indian shield in the lesser Himalayas. It forms dominantly the Sillimanite gneisses protolith in the greater Himalayas, and it forms the base of the Tethyan Himalayas. So the Indian plate was one contiguous plate. There is absolutely no evidence of a suture zone along the main central thrust, as has been proposed by some paleomagnetic papers in the literature. Okay, so to put a summary here, we have the biggest ophiolite abducted onto the northern margin of India is the Spontang ophiolite in Ladakh, and this has a uranium-lead zircon age of 177. It's an old Jurassic ophiolite, and it could be one of the very, very few ophiolites that has a mid-ocean ridge basalt-type geochemistry. This is because it's preserved. There's an island ark built on top of it, the Spong Ark, which is an andesitic, dacitic island ark built on top of the Morb ophiolite. And this has a uranium-lead zircon age of 88. We think this is indicative of the timing of subduction initiation in the Tethyan Ocean. The Dras is part of the Kurdistan Island Ark, which is a huge island ark, 50, 60 kilometers thick in the western part of the Himalayas, mostly in Pakistan. And you have to have two subduction zones, one underneath the Spong Ark and one underneath the Dras Kurdistan Ark, both different timing. The abduction of the ophelites and the Drast volcanic arc occurred prior to the closure of Neo-Tethys, probably spanning the late Cretaceous and Paleocene. And then finally, the continental collision, which resulted in the huge crustal thickening and metamorphism that we see today along the Himalayas. So in the west, the Kurdistan Island Ark is absolutely unique. It's about a 60-kilometer thick section of crust through a tilted island arc. It shows 120 million years of magnetism, which is quite extraordinarily long. Dominantly calc-alkaline volcanics intruded by I-type granites. These granites are very similar to the Ladakh and the Khoestan and the Gandhisi batholith in South Tibet, biotite hornblende, tonalitic granodioritic rocks. The middle crust is dominantly amphibolites and also intruded by these granites, and the lower crust is composed of a sequence of periddotites, pyroxenites, including the Geological complex garnet granulites, which are the base, the deepest crustal section of the island arc, and the Chilas complex, which is a gabbro-norite sequence that's interpreted as the magma chamber underneath the Kurdistan arc. So all that happened prior to collision. How do you define India-Asia collision? You can define it a number of ways, which have totally different timings. One is the first meeting of continental crust, the basement of India meeting the basement of Asia. This could happen several million years prior to the final collision, which is determined by the final marine sediments along the Indus suture zone and along the northern margin of the Indian plate. The first one we can't really date because you can't see it. The second one we can date, and it has been dated absolutely precisely, from the foraminiferal assemblages in the uppermost, youngest marine sediments beneath the Indus molasse. And these are belonging to the planktonic foram zone P8, which is lower Eocene, 50.5 million years. After 50 million years, there is no evidence of any oceanic sedimentation anywhere along the Indus suture zone or along the northern margin of the Indian plate. So the post-collisional molasse basin is beautifully preserved in Ladakh, and the diagram at the top shows a reconstruction of all the folds and thrusts in this basin, and it shows all the age constraints we have. So in blue are the paleontological ages based on marine foraminiferal sediments. In brown are detrital zircon ages from the continental molasse sediments, and yellow. And in red are the uranium lead zircon ages from the Ladakh granites. And the youngest components of the Ladakh granites are these Chumatang leucogranite dikes, which are truncated at the base of this part of the Indus molasse basin, and they're dated at 47 million years. Okay, so after the India-Asia collision, the whole of the Indian plate started folding and thrusting on a huge scale. And this is just one profile down the Zanskar River in the central part of the Ladakh Himalayas. The profile in this sequence is about 2 to 3 kilometers thick, and it shows spectacular folds and thrusts, southward verging folds and thrusts within the Indian shelf carbonate sequence. These are overlain unconformably by the Paleocene-Eocene sediments here, which are only gently folded, and the ophiolite forms these mountains in the background. So the first effects of the India-Asia collision are usually assigned to the ultra-high pressure eclogites that we see in two main localities. The first is Kagaon in northern Pakistan, and the second is Somarari in Tibet. And these are spectacular eclogites. They contain coesite and supposedly microdiamonds. They have pressures anything up to 28, 29 kilobars, indicative of subduction of continental crust down to depths well over 100 kilometers. This is the outcrop in Khoestan, and these are the Kagaon eclogites with all the geochronology that have been done to constrain the age of subduction of the leading edge of the Indian plate during the collision. And the alanites and zircons, which give you the peak high pressure ages, are about 46 to 47 million years old. The titanites and the rutiles give you very, very closely following that 46 to 44. which means that there is a very rapid exhumation of these eclogites through the mantle during exhumation until they hit the base of the crust. And when they hit the base of the crust at about 10 kilobars here, you have a more gentle cooling curve where the eclogites are entrained in the laser kyanite and sillimanite grade gneisses of the Indian plate. So this is the classic eclogite locality where a lot of the PT work and the dating work has been done, but there are numerous eclogite localities all over this part of Kurdistan. So the cooling paths, the geochronological constraints of the Somarari eclogites in India, again show a very similar trend to Kagan. They show a massively rapid exhumation path from ultra-deep subduction of eclogites until they hit the base of the crust. And at this stage here, at about 10, 12 kilobars, they are entrained in the normal kyanite, sillimanite grade metamorphism along the Greater Himalayan sequence. But the big question tectonically is, are these the final stage of ophiolite abduction, or are they the first effects of continental collision, or, as seems most likely, is that one stage leads straight on to the other? So what does crustal thickening look like in the Himalayas? Well, here is another picture taken from west of the Zanskar Gorge, and this is almost entirely in Triassic-Jurassic unmetamorphosed shelf carbonate sediments. The yellow lines are just picking out folds in the bedding, and the red lines are detachments or thrusts. And this is how you thicken the crust. After continental collision, you thicken the crust by massive isoclinal folding, thrusting, crustal thickening. And as you go deeper and deeper into the section, those rocks are going to be metamorphosed. And this is the beginnings of the greater Himalayan sequence metamorphism that we see. So the entire history of these rocks shows rapid burial by folding and thrusting, clockwise pressure temperature time paths, followed by a decompressional heating during decompression from kyanite to sillimanite, sillimanite plus cordierite. And this is the melting that is related to channel flow. So we're relating a lot of the maximum elevation, maximum crustal thickening, timing of peak metamorphism, anywhere between the kyanite grade timings, which are about 40 to 35 million years, up to the youngest sillimanite grade metamorphism and partial melting of the leucogranites, which are generally around 20, 21 million years, but they do extend down to about 15, 16 million years. And that's the timing of channel flow. So to put this in context, the diagram on the top is the first stage of orogenesis in the Himalayas. It's the Oman ophiolite stage, if you like, where the abduction of the Spontang ophiolite from Tethys onto the passive margin of India has occurred. TM is where the position of the Somarari eclogites is now in the middle crust. And these are the rocks that have to be subducted down to well over 100 kilometers depth at 47, 46 million years old. And at this timing, you're starting to crustally thicken the Indian plate. And when the Somarari eclogites become entrained in the lower crust here, they are entrained within the kyanite, sillimanite grade rocks of the Greater Himalayas, and they follow a similar cooling path. So the peak of the pressures in the kyanite grade rocks, 10 to 12 kilobars, we think occurred between 40 and 35, 32 million years ago at depths, lower crustal depths. And then you have a decompression to sillimanite grade metamorphism, which is higher temperature but lower pressure. And this is when all the mignetization, partial melting and granites fit in. And these form the core of the Himalayas. So this is the channel flow model that was actually first proposed by field mapping in Ladakh and Zanskar and in Bhutan. And this states that the main central thrust zone, which is the base of the channel flow, shows the inverted metamorphism going from structurally the top to the bottom, going from the sillimanite, pegmatites, and leucogranites down through kyanite, staurolite, garnet, biotite, to the brittle thrust of the MCT, the main central thrust at the base. So inverted metamorphism at the base and right way up metamorphism along the Zanskar shear zone or the South Tibet detachment at the top. And both of these ductile shear zones were operating at the same time, generally between 21 and 17, 16 million years. And it's only one place in the entire Himalayas that you can actually physically map and walk on these isograds from the right way up at the top around to the inverted in the base. And that is in the western part of the Indian Himalayas, above the Kishtwar window, where you traverse westwards into the Kashmir Himalayas, where you can actually physically map the inverted isograds swinging around to link up to the right way up isograds beneath the STD. And all of the central zone here in the main part of the Himalayas is sillimanite grade, pegmatites, leucogranites. And in the west, in Zanskar, it's dominantly up here in the kyanite grade fascies. So here is a model of channel flow, the Himalayan channel flow model, which is very distinct and different from the lower crust model, flow model for Tibet. The Himalayan channel flow model is the southwards extrusion of a partially molten layer of mid-crust dominated by sillimanite-grade pegmatites, leucogranites, which in the Everest Himalayas in Nepal have ages around 22, 23 to 20 million years. And as you go towards the north, in the North Himalayan domes via the Amadrima complex, the North Himalayan domes have a younger metamorphism at 14. This is all constrained by geological mapping, combined with pressure temperature work and geochronology. Once you cross into Tibet, you have no deep erosion, so we cannot use any of our geological constraints that we can in the Himalayas. And here we're reliant on geophysics. The geophysics from the in-depth model has showed us that it is absolutely clear that there is a mid-crustal zone of partial melting at extremely high temperatures, with pockets that they are called bright spots on the in-depth profile, which we interpret as actually magmas, Himalayan leucogranites forming today at this time. So you have a younging progression of melting from what we see exposed along the Himalayas through the North Himalayan domes to the presently active zone of metamorphism and partial melting underneath southern Tibet. So this is a mid-crustal layer of extrusion and partial melting. How do we know what the composition of the lower crust is? The lower crust is a series of high-pressure granulites of varying lithologies, and we don't see this geologically. You can't actually physically map it, but what we can see in southern Tibet is a series of these spectacular lamprifier shoshonitic dikes that are intruding at about 12 million years. And they intrude right through. These are mantle-derived melts derived from picking up melting parts of the lower crust. And they have a whole series of xenoliths in them, tiny xenoliths, which have a range of compositions from mafic, ultra-high temperature, ultra-high pressure granulite, well over 1,000 degrees centigrade, 25 kilobars pressure. There's some very strange restitic ultramafics, which are hornblende biotite rocks, and there's some felsic granulites who are a bit high temperatures but slightly lower pressures. And we've picked out xenoliths in these, picked out zircons that you can date using uranium, thorium, lead, and these are all in the range of 16.8 to 14.4. So we know at this time that the crust of the Himalayas was thick, very thick, and very hot. And these xenoliths are the evidence for what is occurring beneath the ductilely extruding channel flow of the mid-crust. Another major tectonic feature of the Himalayas is the South Tibet detachment, which is definitively a low-angle normal fault. This low-angle normal fault has offsets of well over 100 kilometers, as you can see by mapping along the Rongbuk Glacier north of Everest. And it puts unmetamorphosed sedimentary rocks over high-grade metamorphic rocks of the GHS. And Dhaulagiri is one of the only two 8,000 meter peaks, the other one being Annapurna, which is within the Tethyan Shelf carbonates. Most of the other high peaks are down here in the upper part of the Greater Himalayan sequence. And we have three rocks here that we can define the pressures and temperatures from. The rock at the base of Dhawalgiri is an unmetamorphosed Cambrian limestone, so it's never been buried below 2.5 kilobars at the maximum. The second one we have is this tremolite-bearing marble, clinopyroxene tremolite K-feldspar marble. It's the upper amphibolite facies calc-silicate rock that is being metamorphosed at about 9 kilobars and about 600 degrees centigrade. And the final one we have is a kyanite-grade peelite, which is metamorphosed at 10 to 12 kilobars, again at about 600 degrees centigrade. So we've got to get these rocks up to juxtapose next to each other, as we've seen in the profile in the previous slide. And if you assume the South Tibet detachment maintains the same dip as it is today, which is not unreasonable, then these rocks must come from anywhere up to 100 kilometers north of their present situation, and they must have extruded up by a ductile flow mechanism. Beneath the South Tibet detachments in the Himalayas, this is in the Kali Gandaki region of central northwestern Nepal, this is the classic zone of inverted metamorphism, where you go from sillimanite-grade rocks at the top through kyanite-grade rocks down here in Unit 1, series of quartzites, and you're going from sillimanite to kyanite to garnet to biotites as you go structurally down section along the STD. Pictures on the left show the very first initiation of melting, which are these tiny little melt pods containing kyanite. They're K-feldspar poor, so they're dominantly kyanite plus quartz, but they're the first indications of crustal melting at high pressures, 12 kilobars, probably at around 30 million years ago. And then most of the Himalayan melting is in the bottom photograph here, which is the classic sillimanite plus K-feldspar melts. And these produce the granites that are sillimanite. They have magmatic cordierite. Some have magmatic andalusite. So they're high temperature but low pressure. And these melts, the timing of them forms the timing of channel flow along the Himalayas between 24 and 16. So channel flow is not active today, but it was during the late Miocene. As the melts ran out, the leucogranites were intruded and they were carried piggyback by structural propagation down to the lesser Himalayas and the main boundary thrust at the base. So pressure temperature profiles, these profiles are taken across the central part of the Nepal Himalayas, the Everest region, and they all show an increase of pressure and temperature as you go above the main central thrust zone. From the top of the main central thrust zone to the South Tibet detachment, you are maintaining high temperatures above 600, around 700 degrees centigrade. This is all in the huge, thick section of sillimanite-grade gneisses, migmatites and leucogranites at the top. This is a slightly more updated profile where you have pressures and temperatures along strike, and you see from the cross-section above that you have a very narrow section of inverted metamorphism from sillimanite K-feldspar down to garnet grade. This is the main central thrust zone. And then all of the yellow rocks here are in sillimanite grade conditions right the way to the top. And in the Everest series, just below Everest, this is beautifully exposed on the southwest face of Everest. These rocks are in kyanite and staurolite grade, forming the upper part of the right way up metamorphism beneath the Himalayas. And the very summit of Everest, the South Tibet detachment, the Chomolungma detachment, cuts right through that, putting Ordovician limestones unmetamorphosed on top of the high-grade gneisses of the Himalayas. And you can actually physically walk on the South Tibetan detachment, the Chomolungma detachment, from the top of Everest, just below the summit of Everest, all the way down the Rongbuk Glacier for a distance of at least 70 to 80 kilometers. So there is absolutely no question that low-angle normal faults do exist. They were active during metamorphism, active during channel flow, and they formed the passive roof zone beneath which the channel was extruded to the south. And all this is explained. This is my geological map of Everest that was produced in 2003 with 2 cross-sections through the Everest Massif showing this low-angle detachment, low-angle normal fault along the South Tibetan detachment. And these 2 detachments actually merge to the north, where you have a real condensation of metamorphic isograds from sedimentary rocks at the base of the Tethyan sequence down to high-grade rocks at the base. There's 2 major dehydration reactions that produce these granites. The most common one is the Muscovite dehydration reaction, which produces the classic tourmaline garnet to mica Luca granites that we see all along the Himalayas. The second one is a higher temperature reaction, the biotite dehydration reaction, which is occurring at slightly higher temperatures. And this is the one that is common that you see, for example, in the Makalu Massif, where we have these spectacular large cordiarites, which are parts of the Barun migmatites that occur right to the east of Everest through a lot of the profiles there. So that's the major Himalayan story as regards metamorphism and tectonics. There's one crucial exception to this, which is in the far western syntaxis, the Nanga Parbat syntaxis, which has been through the entire pressure temperature tectonic history that I've just described for the Himalayas. But it has an even younger phase of metamorphism, which is superbly documented by these are the youngest uranium-lead monazite and xenotime ages anywhere on the planet. And they're as young as 0.7 million years. These are Pleistocene quaternary migmatites forming cordiarite, sedimentite, garnet, Luca granites today. And that is because Nanga Parbat is constrained to the west by the Kurdistan Ark. The rocks have nowhere to go other than upwards. So if you look at the rocks in detail here, they are high temperature migmatites. The green blobs here are all cordiarite and selimonite. The black are the tourmaline. And most of the core of Nanga Parbat is preserved as these Pleistocene migmatites forming between 3 and 0.7 million years ago today. And this could be indicative of what is actively forming underneath southern Tibet today, underneath the northern part of the Himalayas today, but it's not yet exposed. And the reason they're exposed in Nanga Parbat is because there's a buttressing effect. So the channel flow goes from southward verging in Zanskar and the Indian Himalayas to the east to basically vertical extrusion of this high temperature core of Nanga Parbat bounded to the end. So to finish off 2 profiles, structural profiles, this is across the central part of the Himalayas in Nepal and Tibet. And all of the structural data we have from the high Himalayas require the lower crust, the Indian lower crust, dominantly comprising the Archean granulites of the Indian Shield and the Proterozoic Himalayan metamorphism to extend northwards across Tibet, at least halfway across, 400 or 500 kilometers north of the Himalayas. This is a requirement through the balance and restoration of sections through the Himalayas and a requirement from the geophysics as well. In the Western Himalayas, a little bit more complicated because on the Asian plate here in grey, this is the Baltoro region of the Karakoram. We have a massive Miocene granite batholith intruding in the middle. And all of these grey rocks here are Cenozoic metamorphic rocks, mostly at high grade, kyanite, selimonite grade. And you don't see these rocks in Tibet because they are very low erosion and they have not exhumed up there. So again, requirements of a lot of the transition from granulite to eclogite of the Indian lower crust. And this is backed up by all the geophysics and all of the deep seismic profiles that have been shot across southern Tibet. They all agree that the lower crust and mantle of the Indian place extends northwards at least halfway across the plateau. So you have a cold Indian mantle to the south and a hot Asian mantle to the north. And this corresponds in northern Tibet to where the all active volcanics are erupting today. So the picture in the Himalayas is a nice picture of very steady state orogenic effects. We've had 50, 60 million years of orogenesis, and this is still happening today, as was evidenced by the April 2015 Gorka earthquake, where it showed that the main Himalayan rupture occurred down here underneath the northern parts of the Kathmandu Basin. And this was a thrust fault, which is the active thrust fault on which India is under thrust in the Himalayas today. This earthquake caused a horizontal slip of up to 5 meters. There's about 150 kilometers of the fault zone ruptured, and the whole thing tilted to the north. The big problem was that there was no surface rupture, which means that this massive amounts of strain is built up underneath the central parts of the Nepal Himalayas, and it's just waiting for the next earthquake to release that strain, which will affect one of these active thrusts in the south. So there's a huge danger of future earthquakes in parts of the Himalayas. Okay, thank you very much. And again, an enormous thank you to all the organizers of the IGC in Delhi. It's a great shame that we couldn't give it online, but I look forward to the next conference we have in India. Thank you very much.
Thank you. Thank you very much, Mike. It was very nice. In such a short time, you could cover the whole gamut of things in the Himalayas. Just for the audience to know that me and Mike, we were together as postdoc at University of Leicester. I was working with John Tarney, and he was doing work with Brian Bindley. From that time onwards, we have been working, and still we are working with one of the PhD scholar working with us. So thank you so much, Mike, and we look forward that we will be again getting chance to come physically to the Himalayas and do some work. Thank you so much. So now I have the pleasure to introduce Mike Wickel. He is a fellow of the Royal Society and emeritus professor at the Department of Earth Sciences in Cambridge. Mike is again one of my collaborators, and we have done lots of work with him. His main interest that you all should know that he has worked on the tectonics and climate control on the silicate weathering in the Himalayas and other parts of the world, magnesium isotope budget of the modern ocean, constraints from riverine studies. Now he's going to talk also on the geological carbon storage, which is going to be very interesting, fluid flows and CO2 fluid and mineral interaction during the CO2 storage in the sedimentary basins, relative contribution of silicate and carbonate rocks to the riverine strontium flux in the headwater of Ganges, isotopic constraints on the structural relationship between lesser Himalayas and the higher Himalayas that we did together, volume and many other things, obviously. And then very, very interesting. He started with very hard rock, Archean rocks, and he did very good paper with the volume and composition of melt generated from the extraction of lithosphere and extension. Similarly, potentials of Archean mantle, evidence from Komachild. So those were very highly cited papers. And then the Himalayan metamorphic CO2 flux, quantitative constraints on the hydrogen. And recently, we have worked on the eclogites using the isotopes and then putting constraints on their protoliths. So these are some of the, although Mike again has a very long list of publication and lots of interest in right from Archean to the present. So I welcome you, Mike, and please make your presentation. Thank you so much.
Thank you, Tala. Okay, can you make that full screen? Great.
Yes.
Okay, well, again, I'd like very much to thank the organizers of IGC, who had an enormously difficult job with the cancellation of the in-person meeting and have finally managed to put on this virtual meeting. I'd also like to thank all the people who I've collaborated with on this work on geological carbon storage listed on this slide. And they're, of course, are the people who've done practically all the work. Well, geological carbon storage is going to be essential if we're going to limit the impacts of climate change. And the next slide shows why. Can I have the next slide, please? As you can see on the left, the emissions have carried on unabated, and the only thing that impacts emissions are a series of financial crashes, for example, 2008, small dip, or COVID, which caused a rather larger dip in 2020, but never mind, emissions are recovering nicely. And the result is that atmospheric CO2 levels shown on the right are going up exponentially with no diminution at all. So what are we going to do about it? On the next slide, top left, we can see models for trying to keep temperature rises by 2050 down to 1.5 degrees or 2 degrees. The brown curve shows what we need to do if we have little removal of CO2 from the atmosphere. We have to cut, this is emissions, we have to cut emissions drastically starting in 2020 and going down virtually to zero by 2030. Well, it's already 2022. We've made no dent in cutting emissions. It's really significant. And you can see that even for 1.5 degrees, if we have high CO carbon removal, or 2 degrees with moderate carbon removal, we still have to start working on it. The result is we're going to overshoot significantly on climate change. We're not going to make these targets. The lower graph on the left shows the amount of carbon removal needed. This is in gigatons of carbon, not gigatons of CO2. And it's suggesting to make the targets shown above, we need at least 2 to 4 gigatons of carbon removal by 2050. The reality is we're going to need much more. And we can do some of that by moderating the surface, growing forests, but I think that's rather dubious. We need to grow forests to replace the ones we're cutting down. We won't have nearly enough capacity. We're going to need geological carbon storage. And the next question is there enough capacity? The map on the right shows an estimate of Indian carbon storage. In saline aquifers, there's an estimate there's about 80 gigatons of carbon storage available, and then maybe similar amounts in basalt. So that's much less well researched. The problem is we don't know really much about these potential storage sites. Well, is geological carbon storage safe? Does it work? The next slide shows us properties of CO2. And CO2 is rather a fun fluid. It has a critical point at quite moderate temperatures, 31 degrees, 7.4 megapascals. That's about 740 meters water depth. So above pressures above that, temperatures above that, CO2 is a supercritical fluid. And we can look at the density properties on the right, density against temperature. And we can see that if we go above the critical point, densities increase quite markedly. And if we look at a typical geothermal gradient along which we might store CO2, if we go deeper than about 750 meters, 800 meters, pressures of 8 megapascals, the CO2 density is about 0.8. It's lighter, less dense than water. So when we inject it in the ground, it'll tend to rise. We need to trap it somehow, but it's quite dense, so we can store it moderately efficiently. The next slide shows a successful attempt at CO2 storage. And there's a series of large projects that have successfully injected CO2 for quite a while. One of the best known and oldest is Sleipner in the North Sea, which now stores about 16 million tons of CO2 at depths of 800 meters and more. They started this storage because there's significant gas and the gas they're extracting from greater depths. Norway put a tax on CO2 emissions, so it's cheaper to storage. It shows a small tax on CO2 emissions can make a big difference to CO2 emissions. And here they pumped it down and stored it into Sierra Formation, a very porous sandstone. And on the right, you can see seismic images of this. The bright spots are where we have CO2 stored. It caused significant reflections. And in fact, it illuminates the structure of the reservoir. There's a series of thin mud horizons in the reservoir, less than a meter or so thick. CO2 pools under these before escaping towards the top of the reservoir. The next slide shows we can do simple modeling of the reservoir. And the two left-hand images show structure of the reservoir, cap rock topography. It forms a shallow dome that traps the CO2. It's rather elongate. The next slide shows the thickness of the CO2. No, go back. The next picture shows the thickness of that top layer. And then we can measure the thickness of the CO2 there. The top slide shows thickness of CO2 against a color scale at the bottom. And you can see its thickness in this top layer goes up to about 12 meters. And the thickness estimates are by some rather clever seismics done by one of our students, Lawrence Cowton. And then we can model the thickness of this. And again, what we want to do is understand the structure of the reservoir, and no constant permeability model gives us this structure. So using a simple vertically integrated flow simulations that we can do lots of computations on, unlike numerical modeling of reservoirs, which involve large meter or 10 meter scale blocks that take a lot of computer time, we can basically calculate a permeability that fits this structure. And the permeability structure it comes up with is a high permeability channel with a 20 Darcy permeability versus the average reservoir of 3.5. And the lower diagram on the right shows the successful runs that mimic the image CO2 very nicely. Okay, so large scale CO2 storage works. And importantly, we can infer quite a lot about reservoir properties if we can observe our data nicely. And that's going to be important for understanding more about reservoir behavior. So what are the problems? The next slide shows on the top left some of the problems that people come up. And the first one is, will the CO2 or CO2 dissolved in brine forming carbonic acid corrode cap rocks? I'll come back to that briefly. Will it migrate up faults, and what happens? And some other potential problems. Will it cause overpressure that causes earthquakes? What about old drill holes? Well, we can avoid those by not overpressuring our reservoirs, sealing old drill holes. But against those potential problems, there's a series of processes that stabilize storage. The first, and volumetrically probably most important, is residual capillary trapping. This is shown bottom left, where we've got a X-ray 3D microtomography image of a core experiment. The red are minerals, mainly quartz. The core was flooded with CO2 till it was virtually saturated. Then it was flooded with water. But you can still see there's some CO2 left trapped. Those are the dark images in the X-ray, and the green is the brine that's flooded the core. But basically, somewhere between 20 and 30% of the CO2 remains trapped. So if we have a CO2 plume migrating, it leaves a lot of itself behind. And this is a model in the middle right, where Mark Hess and students injected a volume of CO2 and then let it flow up a model aquifer for 3,000 years. And after 3,000 years, 70% remains trapped, and the live CO2, the red bit on the diagram, is still flowing upwards. So that's one form of trapping. And we know that'll work quite well. Second trapping, which we understand much less about, is the CO2 will dissolve in the brines. And when it dissolves, you can dissolve 4 or 5% CO2 in brine by weight. It makes the saturated brine denser, so it'll sink, which is a good thing from storage potential. Some of this sinking may cause convective mixing. We may also get reaction between brines and minerals in the reservoir. They're surprisingly fast, and particularly in basalts, they've been shown in Iceland to become a dominant form of storage, but less so in silicate reservoirs. Well, what I want to do, so it's quite possible that we can store CO2 in unconfined aquifers, and this could be important for big countries, both like China or India, with a lot of offshore storage, but not necessarily well endowed with closed traps. But anyway, for the rest of the talk, I want to talk about dissolution trapping. And this is very poorly understood because the scale of dissolution depends on diffusion distances that are centimeters, whereas nearly all reservoir models are on scales of meters or tens of meters. They can't model dissolution trapping. And if they tell you they are, they're lying, basically. So let's have a look. And the only way we can study at the moment is by looking at some natural analogues. And we've been working on the Colorado Plateau, where there's a whole series of natural CO2 reservoirs. These are shown in blue on the map. Most of these are sealed, they don't leak, and they've been extensively exploited, and the CO2 taken off mainly to Texas for enhanced oil recovery. One of them at Green River in Utah, top left of these states, for those people who don't know their US states well, is leaking. Some of it's leaking shown on the right, and there's a spectacular geyser that goes off every once or twice a day. This is where they drilled an oil well or an oil exploration well in the 1930s. As you can see by the pipe sticking out of the ground, they discovered CO2, so they left it open, and it's tapping CO2 at a depth of several kilometers. And obviously, if you have a CO2 store, one thing not to do if you don't want it to leak is drill holes into it and leave them open, which is, of course, rather obvious. Anyway, we've looked much more detail at CO2 in Green River. It's been leaking naturally for hundreds of thousands of years. And the next slide shows the hydrological setup at Green River. Next slide. We have San Rafael Swell, a rather scenic area to the northwest with a big monocline. Aquifers there are recharged by rainwater that flows towards the southeast. It intersects a series of faults forming small grabens that have formed fairly recently, and CO2 has been leaking up these, forming travertines along the fault scarps that you can date using uranium lead. As I said, there have been a series of holes drilled, water exploration holes, oil wells, particularly the deep crystal geyser well. And then we shell drilled a hole for us to investigate the hydrology and the CO2 in the Navajo Formation. That's the second permeable formation shown there. Well, the next slide shows the exposed rocks. This is the upper formation where it's exposed by faulting along grabens. You can see the fault on the left-hand side where it says extensional fault, and that fault basically runs along the front of this cliff. So we're looking back at the footwall. Just covering the fault is a travertine mound outlined by white dots. And then we have the downthrow side rocks further to the west. But in the Entrada Formation, it's basically a red hematite-bearing Aeolian sandstone, and the bottom of it is significantly bleached. And this bleaching was caused by CO2-saturated brines leaking out from the faults. And these brines are CO2 saturated. They're also sulfate bearing, but also contain a small amount of sulfide. They're slightly reduced. And the reducing fluids basically reduce the hematite, causing the bleaching. We can also see the bleach zones escaping up small faults and fractures in the photographs below on a number of scales. So this is basically what's happening. CO2 saturated brines were leaking out when these rocks are buried at depth. Presumably also free CO2 was leaking out along the top of the formation, but we don't see that. The next slide shows the drill site. And two of the reasons for drilling, one was to sample the cap rock, base of the Carmel Formation. And we worked on that, and we've shown that the CO2 reactions with the underlying fluid only extend 3 or 4 centimeters into the cap rock, and this is over a time scale of 100,000 years or more. And secondly, the fluid rock reactions actually decrease the permeability of the cap rock, which is very slow, by precipitating minerals. That's been done and published. The next thing we did was when we drilled, we sampled fluids to see what the CO2 content did. And on top right, we show high pressure sampling of the fluids. We did pH measurements of pressure, and we titrated for total CO2 at pressure. The other thing to note, bottom left, is that the core we recovered from this reservoir is all bleached. Normally the Navajo were exposed as a delightfully red hematite sandstone. Where you've had CO2 brines, it's bleached. Okay, we look at the composition of the fluids we sampled on the next slide. And as I said, we could measure CO2 contents by 2 methods: CO2 from titration with potassium hydroxide, CO2 from measuring pH at pressure and alkalinity. And they do agree nicely. And to our surprise, the fluids from the bottom are actually CO2 saturated. They drop below saturation towards the top. And what this means is, since CO2 saturation drops off significantly with pressure at these shallow depths, we're only down at 300 meters, the brines coming up the fault zone must be degassing free CO2 as they come. So let's look at a model for CO2 flow of the brines and CO2 on the fault zone in the next slide. And we can see we've got the major fault and maybe a minor fault that cut the drill core cut. We must have CO2 charged brines that are flowing along the bottom of the reservoir, like in the Entrada. They're denser because they're more brine rich, and they're denser because they contain a lot of CO2. CO2 will be escaping and flowing along the top of the reservoir. When drilling, we also encountered significant CO2 in the Entrada sandstone, which was a surprise to us because it's really open to the surface. Also a surprise to the drillers, slight embarrassment as it's a drill pipe blew out of the drilling, but we're not really meant to talk about that. So it shows in these heterogeneous formations, CO2 is actually surprisingly well retained. So can we model this? The next slide shows numerical modeling of the CO2 flow. This is one of the tough two grid type models. And what we've got here, that's the 3D block diagram, but the groundwater flow, which is measured by numerous measurements of groundwater head in the shallow water wells and so on, is actually flowing along the fault system here. And we can model it by having a section of injection of CO2 brines from the faults along about 2 kilometers. And in this situation where we've got groundwater flow, if the brines flow out from the fault for any significant length of time, more than 1,000 years or so, you get a steady state situation where the rate of flow outwards is balanced by flow along. So the brine plume, if you like, extends a limited distance, which is a function of the flow along the fault and the amount of brine coming out. It goes on extending and expanding downwards through time. This means we can use the extent to calculate the rate of flow of brine out of the fault, which is about 0.4 meters a year. And the next slide shows that we can then quantify the amount of brine coming out and work out how far it comes out. So we've got, top right diagram shows we've got about 2.4 by 10 to 5 meter cubes of brine flowing out of the fault. That's carrying about 6,000 tons of CO2 a year into the Navajo Formation. Top left, we can look at the model saturation in this model, and we can see that the fluids on the left are saturated and the plume extends as far as shown in terms of distance of the fault. Saturation's high in the reservoir, are higher in the model. This is partly because we have free CO2 degassing, probably dissolving in the brines up there, shown bottom right. Also, because the reservoir is heterogeneous, so the simple flow model in a uniform reservoir won't capture the fact there's order of magnitude permeability differences in the sandstone. Although it's a homogeneous sandstone, even the most homogeneous sandstones have these permeability variations. And that makes actually a lot of difference to the CO2 flow. Well, we've got a measure of how much CO2 comes out in this horizon. If we go to the next slide, we can calculate what will escape to the surface. And as is typical, you can see we have 3 or 4 permeable horizons here: White Rim Sandstone, Wingate Sandstone, Navajo Sandstone, Entrada. We're looking at the Navajo. If we had CO2 flowing out at the rate we've calculated, 6,000 tons a year of CO2 coming up in brines in the fault. Most of that flows out into the Navajo, in fact, so we lose 94% of that into the Navajo. If we then had it going through another aquifer, we'd only have 360 tons escaping. Again, most of that would be lost into the aquifer. And by the time we get to the surface, we have about 1.3 tons a year. This is consistent with long-term emissions at the surface, which has been estimated from travertines by Burnside et al., who dated them, did volume estimates and groundwater flow rates. And what it means is you have 3 aquifers, each time you get a sort of power law reduction in CO2 escaping. So even if we have a fault zone with significant sea coming up, go through 3 aquifers, we only find that 0.02% of the CO2 escapes at the top. That's very long. So this is a good field example that dissolution could be really significant in stabilizing CO2 in storage reservoirs. And as I noticed, time is running out. There's not time to talk about a lot more. So if I go to my concluding slide, geological CO2 storage is going to be safe, secure. It's been demonstrated. And in fact, these additional trapping mechanisms, capillary and dissolution trapping, will probably make unconfined aquifers safe. They'll basically make it cheaper because they'll decrease the risk. And when we have CO2 at storage at scale, storing 10 gigatons or more of carbon a year, i.e. the same scale we're emitting it now, small changes in cost are going to be very important for society. There's a lot more work to be done on understanding the controls on dissolution trapping, capillary trapping, particularly the impact of rock heterogeneities. It's very difficult to do in models. We can model it, but we need to do field experiments to recover what actually happens. And that is going to be very important. Anyway, thank you very much.
Thank you very much, Mike.
Okay.
It was an excellent talk. The type of work that Mike and his group has done, which has lots of importance for and for the survival of the society. Now, if we do this sort of research, then in future we may have some answers to the problem of this carbon dioxide and the temperature. Thank you, Mike. It was very nice to see you also, and I hope that in Himalayas still, now that pandemic is gone, looks like this is gone. And for the audience, if they have any query or questions, they can put it in writing, replying to their queries. So I thank you all, and I thank you for such good presentation. Thank you so much. हाँ संगीता, अब मैं आगे वाला प्रोग्राम इसी पर कर सकता हूँ या मैं फिर से डीलिंग करके वो दूसरे में जाऊँ?
Okay, we are live. So, sir, we are live now.
Okay. Okay, wonderful.
Start your
Okay. Martin, I'll introduce you to the audience. Martin van Canendorp is a professor of geology and astrobiology at the University of New South Wales, Sydney, and is the director of the Australian Centre for Astrobiology. Martin is Canadian by birth and training. He moved to Australia in 2012 and studied the early sign of life on Earth, nearly of 3 billion years older rock, in old rock. As his researches have been used by NASA and European space agencies for the search of life in Mars. He has got many publications to his credit, and he is very well respected Precambrian paleontologist of the world. Okay, Martin, you start.
Thank you so much for the introduction and for the honor of giving a talk here at the IGC.
Welcome to this talk on microbial life on an alien world, the habitats of life on early Earth. My name's Martin van Canendorp, and I'm the director of the Australian Centre for Astrobiology at the University of New South Wales in Sydney, and it's my great pleasure to be invited to give this talk for the IGC, and I wish I could be there, but at least we got this opportunity to keep going. So, what do I mean about that? Well, you know, the origin of life, the spark for life, is still unknown. If we knew it, it would be a Nobel Prize, of course, and there would be a lot of excitement, but there's a lot of information that's being gathered as we move to a better understanding of this very complex topic. And everyone would agree that the road to making life is extraordinarily complex. Many different reactions, complex geochemistry, and a reaction space that probably requires not just a linear sequence of steps, but probably a very complex interactions of different components being formed in different places and then mixing together to get, you know, primitive life, even still extraordinarily complex. And most have considered over time that this is a very long process. But if we look at the geological record, there may be some surprises in store about that, because the idea now is that the late heavy meteorite bombardment affected Earth until about 3.9 billion years ago, when high energy, large impacts impacted into our planet and caused sometimes evaporation of the hydrosphere, great heating of the atmosphere, and, you know, destruction of the crust. But after about 3.9, we know that there was a cool early Earth, and our first instances of life coming into the geological record are at 3.7 with stromatolites discovered at Ishua, or at 3.5 in the Pilbara. At any rate, the gap between the end of the late heavy bombardment and the first evidence for life recorded is only about 200 million years, or maybe a little bit more. And so it appears that life got started very rapidly on its way to developing more complex life as we know it from the geological record and on our modern world. But in what environments did that life get started? Well, there are two dominant hypotheses which have actually a lot of similar components that focus around the interaction between hot water and rock, making geochemical complexity. On the one hand, we have the situation in the deep oceans where water circulates through cracks in the oceanic crust, interacts with the basaltic crust, and then returns to the surface in either hot black smokers or warm white smokers, which are more alkaline in composition. On the other hand, we have the idea that perhaps life got started in hot springs on land, where there's also hot water rock interaction, But instead of the oceans, we have isolated pools or fields of geothermal environments. And so what we're interested then is really two main components. How do we look at this? We look at it in terms of the ability to generate chemical complexity, and perhaps through the geological record to look for clues from the habitats of primitive life. In the first case, we know that the models for origin of life at deep sea vents, hot water rock interaction can produce some complex chemistry, including the formation of organic molecules, and these reactions that have generated a lot of excitement about this idea in the literature. But there's a problem with an origin of life in the oceans, and it's called the water problem. It's counterintuitive, but to make the earliest molecules, the energy for bonding simple molecules into more complex molecules comes from being able to eject a water molecule. That gives the energy to bind the molecules together from simple amino acids to proteins, from sugars to carbohydrates, and from sugars with base pairs into nucleic acids. You can see it's the ability to kick out water that drives it. So you need wet-dry cycles. And as a colleague of mine, David Deemer, wrote in 2011, you can heat a solution of amino acids in water forever, but no polymers will produce. On the other hand, polymer synthesis can occur if the amino acids are in a dry state. The source of energy is that water molecules have the potential to leave the system. In fact, if you add complex molecules into water, they break down unless they're protected by membranes of life and so forth. There are many other components about an ocean model that are problematic. So we just heard that the oceans are too wet. The oceans are also too salty for a number of reasons. They're too dilute. Any components that are made are then lost into this vast homogeneous reservoir. And so it turns out that the oceans may not have been the setting for the origin of life. Instead, many people are now advocating for an origin of life on land, where wet-dry cycling through geyser eruption, through evaporation, through the physical upwelling and downdraw of water can cause wet-dry cycles to produce these complex polymers, including RNA. And the other thing that hot springs have is the ability to concentrate elements. Because they're not dilute and because they're geochemically so variable, some pools get enriched in boron, some in arsenic, some in sulfur, some in iron. We have examples of all of these on the modern Earth. And it's this kind of aspect in pools that are separated sometimes only by tens of meters that's so exciting about generating geochemical complexity. Hydrothermal pools on land are also made of fresh water, and that provides the ability to make these lipid vesicles, the protocell membranes that in fact can encapsulate and concentrate organic matter. In the oceans, this process doesn't work because the salt breaks down those membranes, as David Deemer has shown. And in particular, hot springs have the ability to exchange information and generate more complexity because of the variability at the surface. And here's one of my favorite examples from Rotorua in New Zealand. This is Champagne Pool, which is neutral pH, about 70 degrees Celsius. It's precipitating gold and arsenic and has cyanobacteria around its margins. But over this beautiful wet sinter terrace, it's exchanging information with a highly acidic pool, pH of 2.5, a hot pool, and here you can see the sulfur precipitating out. There's an exchange of information that promotes chemical and energetics diversity. So we're very excited about hot springs, as many people are, about a potential site for the origin of life. But what about the geological record? What does that tell us in terms of having a look at what kind of habitats did the most primitive life on Earth form? And the best place to go and study that is in the Pilbara of Western Australia. Now, we're used to seeing our planet in the modern world as this beautiful blue marble with green vegetated continents, drier brown desert areas, and fluffy white clouds. But if we travel back 3.5 billion years ago, we get a very different picture of early Earth. If I was able to sit on a pier sipping pina coladas looking out over the ocean, I would see a green sea rich in dissolved iron. The clouds would be orange because the light filtering through a dominantly CO2-rich atmosphere would give this orangish color rather than the blue and the white clouds. And the land masses would be black volcanic land masses, not the vegetated covered conditions. And so if we could look at Earth from space, we'd see a green planet with small black continental land masses and fluffy orange clouds. So with our knowledge of early Earth, we're able to time travel back to when our planet was actually an alien world. The rocks of the Pilbara, and especially in this area called the North Pole Dome, an area of circular outcroppings in rocks that are 3.5 billion years ago, they preserve the remnants of the geology extraordinarily well. There are similar aged rocks in India, of course, at 3.5 billion years, but they're more highly metamorphosed. They've been heated and recrystallized, but in the Pilbara, we can see the traces of ancient life by these squiggly and domal structures. We can see the ancient ripples preserved on the shoreline of a caldera, and we can see beautiful round evaporative crystal splays that show the evaporation of the seawater so very long ago. We can actually walk on the shoreline where the earliest life was inhabited and get a feeling for what that environment was like. So it turns out the Dresser Formation is a package of rocks here in bloom, just tilted on their side about 30 degrees. And underneath it, in the black, is this extensive network of hydrothermal silica plus barite veins. It's a dense network of fractures that were filled by circulating fluids at the time 3.5 billion years ago, and they have now frozen in place as these veins with beautifully laminated quartz and chert and barite crystals that you can see here. The basaltic rocks that are normally dark green and brown that make the dominant lithology of the North Pole caldera are now altered to this pure white clay-bearing material. You can still see the pillow structures, and this has all the hallmarks of a typical, very shallow system of hot water rock interaction. And it's this environment that we find this ancient evidence of life. We've been able to reconstruct the history of that area as the surface expanded up to near the sea level. There was a volcanic eruption and then a caldera collapse and this extensive hydrothermal network. The stromatolites flourished at this period through here when that environment looked very much like this modern analog from Tonga, this big crater lake with a few islands, very shallow water, and stromatolites inhabiting the shoreline. Very similar to what we see for the ancient Pilbara rocks. And we've been able to document through a colleague of mine, Raphael Baumgartner, who was a postdoc at the University of New South Wales, that these ancient stromatolites on the surface, when you looked at fresh samples from drill core and analyzed them at very fine detail, we were actually able to find remnants of the organic matter that life made as these structures were being deposited, confirming that they are made by biological processes. And then, as we looked in more detail, we found a number of features that indicated that these stromatolites lived at hot springs. A PhD student of mine, Tara Jokic, shown here, found this little rock sample only a few centimeters across that contain very characteristic dark light laminations that are one-to-one found in modern hot spring centers. In fact, this little rock sample, it was deposited from a geyser, splashing hot water exposed on the surface of the Earth. And this was really exciting because we know from modern environments that we can find the associated minerals of The black and white banding are made of anatase and kaolinite, and this is from a modern hot spring in Iceland. So modern equals ancient over 3.5 billion years. And this provided evidence for the wet-dry cycling and clay, which is so important in terms of templating organic molecules in this ancient environment. What we also found when we looked at some of the layers is we found these laminae that were rich in boron-bearing crystals known as tourmaline. Here they are shown very close up. And these have a very distinctive composition in terms of their boron isotopes, shown here in red, which proves that these are not just pure marine deposits, but they actually were on land from hot springs. And modern boron-rich springs are known from India in Puga. And so we feel that these stromatolites were living in these ancient hot spring environments, some of which were concentrated in boron. In other springs, we found enrichments of zinc in the stromatolitic laminae, and also of arsenic and sulfur and iron, elements that are important for prebiotic chemistry. And so we've been able to recreate this environment so very long ago, where the most primitive life was flourishing at the surface and associated with subsurface concentration of elements important for prebiotic chemistry, including the alteration mineralogy that we know is important for templating some of the reactions to make more complex organic molecules. And so by combining our knowledge of the ancient with our knowledge of the deep time, we can find these environments that are not only suitable for harboring ancient life, but are indicative of environments that were present on early Earth where life may have got started. And this has important implications for astrobiology and the search for life on Mars, because on that ancient planet, with crust exposed between 4 and 3.5 billion years ago, have been found deposits from hot springs. And so we're excited to be able to present this idea, and I now am happy to pass over to my colleague Kathleen Campbell, who will develop this idea further. Thank you very much.
Hello, I welcome Kathy Campbell. Kathy Campbell.
Thank you.
She is a full professor of geology and astrobiology at the University of Auckland. She is a paleoecologist and studied interactions of ancient organisms with wide-ranging environments. Her major contributions involved around the possibility of life in Mars. She studied the crustal, fluid, biota, and sediment interactions in extreme environments. This is her specialty. I welcome Kathy. You start your video.
Thank you very much, everyone. I appreciate the opportunity to come present our results. Kia ora. I'm Professor Kathy Campbell from the University of Auckland, and I'm honored to be able to give this presentation today to you in regards to hot springs and the search for life on Mars. I'm also part of the School of Environment at the university and the Te Ao Marama Center for Fundamental Inquiry, which explores the origin and evolution of the universe and its life. So let's continue on from Martin van Kranendonk's presentation, where he spoke about early Earth, shown here in an artist's rendition, And let's start comparing this to early Mars. And some of the key features 3.5 billion years ago were that both planets were anoxic, both had active volcanoes and extraterrestrial impacts that would create heat and liquid water on the planetary surfaces. So the question then becomes, where we put water and heat together on Earth, we get hot springs, and on Earth, where there is hot water, there is life, particularly extremophile microbial life. What about on Mars? Could that have been happening 3.5 billion years ago or earlier? And in the 2004 to 2011 timeframe, we see that NASA Spirit rover was exploring Gusev Crater, particularly around Columbia Hills. And when it came to a place where there were volcaniclastic sediments, reworked ashes here at this site called Home Plate, the rover, as shown here in its final resting point, discovered some very important light-colored whitish features that were determined to be silica. And they're shown with these dashed lines on the side of Home Plate. And the rover found that these silica-rich deposits were in fact had a funny morphology, an unusual morphology. They were finger-like or digitate in shape. The thermal spectra of the emissions on the TES, the thermal emission spectra instrument on the rover, determined that the closest match to this silica was indeed from Earth examples, hydrothermal silica, and in particular, silicious hot spring deposits, also known as sinter. So the Home Plate silica outcrop spectrum shown here, typical spectrum shown here in black, and its closest match on Earth is sinter from El Tateo in the Chilean Andes, and also compared to Yellowstone sinter. The closest mineralogical match was opal A, or non-crystalline opal, plus halite, or rock salt. Now let's talk a little bit about hot springs and why they're important in the search for life on Mars. Well, hot spring extremophile microbes are abundant in hot springs on Earth and adapted to life at high temperatures. So they could have, similar organisms could have inhabited extreme environments of early Mars where there was heat, volcanism, impacts, and water, and hot springs. You can see these lush microbial communities in all these different colors, these bright colors, and they are in fact preserved within the silica that's dissolved in the hot spring waters, which you can see here drying out on these banks up here, and also in and amongst the microbial mats. This is in the summertime, and the mats dry out, and they are infused with silica, which preserves distinctive textures that tell us something about the environment. And here's an example that's 60 years old. It's a silicified hot spring from New Zealand, showing clearly these microbial fabrics and even their pigments still exposed and preserved. So Earth analog studies of hydrothermal deposits are important to help us identify potential Martian textural biosignatures, which are largely microbial in hot springs, for a sample return mission. There are two dominant types of silica-rich hot spring fluid chemistries. Left, you see acid sulfate hot springs, low pH, mainly destructional features, meaning that there's a lot of corrosion from the acid and remobilization of silica from volcaniclastic deposits, with very thin sinters that form, as well as other mineralogies like sulfur, shown here in bright yellow. We also see on the right alkali chloride sinters and hot springs of near neutral to high pH. They form constructional features of almost pure silica composition. And we see here these big sinter aprons, thick sinter aprons that are forming draped in these colorful microbial mats. Now, geothermal systems and active volcanic terrains have variable distributions of different kinds of fluids and deposits, with the recirculating meteoric groundwater being heated up and convecting upwards when coming into contact with shallow magma chambers. If those fluids then collect carbon dioxide, hydrogen sulfide, and salt, and the rock-water interactions then the fluids acquire solutes and also dissolve silica from the country rock. If that rises straight up to the surface and discharges, then we have chloride waters, boiling springs, geysers, and clear waters, and thick centers forming in these outflow areas. In areas where there's been a chance for two-phase boiling to occur in the shallow subsurface, then hydrogen sulfide rises with the steam, creating an acidic steam condensate when it mixes with shallow groundwater to form the steaming ground, fumaroles, mud pots, and collapse pits of acid springs with acid sulfate waters and thin centers. In the alkali chloride system, we have sedimentary facies, models that have been developed over many years by various research groups, including my own, where we have clear temperature and pH temperature gradient from the proximal apron close to or above 100 degrees Celsius going out to the geothermally influenced marsh areas at around ambient temperatures. And the center that forms in these center aprons from proximal, middle apron, distal, and out to the marshes have many kinds of microbial mats that are preserved in the silica, and then give us these predictable textural distributions in these gradients, which we can then apply in models, for example, on Mars, and searching for hydrothermal silica type signatures, morphological signatures on Mars that may tell us that there were microbes present. And even in the vent areas themselves, which don't show any visible signs of, or very few visible signs of microbial mats, there are in fact microbial biofilms that are involved in the formation of features, growth features that are particularly diagnostic of the vent area. For example, different kinds of geyserite, nodular, spicular, the needle-like form, and even radiating macrobotryoidal geyserite. So these are all different forms of geyserite that form in the vent area. And when studying them with microscopy, with Raman microscopy, and even Jurassic ones that have turned to quartz, we see that in fact in the geyserites at the highest temperature, we have layers of microbial biofilm shown here in green for the carbonaceous biofilms, interlaminated with quartz. So the opal has turned to quartz over time in Earth analog environments. So these layers of microbial biofilm or mats and sediment throughout the center apron with all different types of morphologies, all of which are laminated, are indeed stromatolites, which are extremely important biosedimentary structures that indicate life both in early Earth, and the question is whether they are also occurring on Mars. So one of the most important morphological textures then in exploring Mars, and in particularly Columbia Hills and home plate for possible fossil life, is digitate center. So here we see on the left some hot spring center with microbes from New Zealand, and some detailed photographs taken by Spirit rover on Mars that show these digitate features, and you can see the similarities in the morphology. What we don't know is whether the digitate features on Mars are indeed laminated and whether they contain fossilized microbial filaments or other microbial features. So where do these things form on Earth? Well, on the left, we see some alkali springs in El Tatio in the Andes that have a knobby digitate form. And on the right, from New Zealand, and more acid springs, which have more needle-like or spicular forms. But they're found, these digitate centers, across all different hot spring environments and pHs and temperatures in the discharge channels and around the spring pool rims. So here we have an example where one of our students, Michaela Dobson, mapped out for her BSc honors the distribution of spicular digitate center at an acid sulfate spring at Hell's Gate at Tikateri in New Zealand. And you can see the pool areas are shown in dark blue, and the outflow channels and around the rims of the pool show the digitate or spicular center in green. We also see a patchy distribution of different other types of morphologies and mineralogies, including sulfur shown here in yellow. So this high variability spatially is very important. As Martin has already discussed, the variability in chemistry and spatial distribution of environmental conditions is important in hot springs and controlling the distribution of the microbes and also the digitate center. So here, if we look at home plate from another point of view, from an orbital point of view, and Husband Hill in the Columbia Hills, we can actually see that the distribution of sulfur-rich soils is all over the area, including at home plate. And at the same time, we find opal and silica, the two found together in the same general area. And some believe that, in fact, then the hydrothermal silica might not have really had much life in it on Mars if it were in an acid situation or a more destructional environment. But in fact, we now know from work done by us and by Steve Ruff at Arizona State University, one of our collaborators, that both sulfur-rich soils indicating more acid conditions and opal silica can be found from hot spring activity in modern hot springs and fossil hot springs on Earth. So it is possible to have both and to still also preserve life. We don't have to have alkali chloride springs or acid sulfate springs. Either are possible to contain and preserve life in the silica center. Our studies of digitate center in particular in New Zealand show that they're all laminated. There are laminated or layers, fine layers of silica, and also different types of microbes across all the chemistries and temperatures, from acid sulfate to acid sulfate chloride to acid sulfate bicarbonate and alkali chloride springs. So all chemistries allow for the possibility of stromatolites to form. Kitty Shriyaporn, our student who did this work, our PhD student who did this work, also looked at the microbial community composition across different locations. These are different sites along the bottom. Temperatures within sites from 40 to 80 degrees, and also different water chemistries from more acidic centers on the left and more alkali chloride centers on the right, from pHs of 2 to 8. And you can see that the microorganism communities are highly variable and controlled by pH. And but digitate center is found and microbes are found in all these chemistries and all these temperatures. She also found that some of these organisms are adapted to high temperatures, showing evidence of genome streamlining, as well as thermostable amino acids and nitrogenous bases. So the adaptations are there in these communities on Earth. Now, looking also at the digitate center Mars analogs for their material properties to understand more about how they form and how easy or hard would it be to sample these with a rover, for a sample or a fetch rover to go back to Mars and collect them at Columbia Hills. We had a BSc honors student, Emma Nursensova, who studied some of the material properties, hardness and density and porosity of some of these digitate features here at Mars Pool in the Rotakawa geothermal area with micro CT scanning. And we can see in a video internal density changes. This is density being shown with the warmer colors being more dense layers and the more purple colors being less dense layers. And this is a 3D scan through one of the spicules at Mars Pool, showing clearly the lamination. And now we're studying the possible causes for this lamination, either it being slight compositional differences, for example, in water content or organic material, since it turns out that backscatter electron studies have shown that it's pretty much all silica, or there may be smaller pore spaces, smaller than the 2.5 pixel size limit that we have with this micro CT scanning. So we're doing additional work to try to understand more about how these materials grow. We have also in the past grown spicules and digitate center on slides. An example here from Champagne Pool at the Waiatapu geothermal area, where you can clearly see the silicifying microbial filaments. And at the tip of this one spicule, we also see these folded layers of silicifying microbial exopolymeric substance, which is exuded by the microbes to protect them in the environment. So the entire feature is a small microstromatolite that's being silicified over time. And we grew these things over several months to determine growth rates and the relationship between the silica and the filaments. So in summary, stromatolites are like these are important both in early Earth environments and in the search for past life on Mars. Obviously, there are morphological differences between the Martian samples and the Earth samples, but we don't know if they're laminated on Mars or if they contain microbes. Sample return would be needed to determine whether fossil microbes are preserved in hydrothermal silica from Columbia Hills or other locations of hydrothermal silica on Mars. Thank you very much for your attention. Much appreciated.
Hello, excellent, Kathleen. It was excellent talk. It was very nice.
Thank you very much. Thank you.
Okay, thank you. We enjoyed, and I think I will ask the viewers to send their questions if they have any. And in fact, the stromatolite has been one of my most liked subject. I have been studying stromatolites last 50 years in different Precambrian rocks of the world. So it is a very interesting work what you have done. And with the new technology, you are able to see microscopic things, and it is very interesting. Thank you.
Thank you.
Oh, Mihir, please get into now. Okay.
Yes, I'm here.
Okay. Now I will like to introduce Mihir Shah. He is a resident of Delhi, and he is I can say we come from the same city. He is a distinguished professor at the Shiv Nagar University in New Delhi, and is by training an economist, but has spent over 3 decades working in remote central tribal areas of India, forging a new paradigm of inclusive and sustainable development and strengthening Indian democracy through initiatives for people empowerment, especially led by women. He was member of the Planning Commission of the Government of India. He is the founding signatory of the Geneva Actions on Human Water Security 2007. He has many achievements to his credit there, and it will be difficult to say all of them and to tell everybody and his achievements. His partner, Uma Sleka, is a co-leader of Aquadam, which is the Advanced Center for Water Resources Development and Management. She is engaged in demystification of the science of hydrogeology, providing key inputs into the groundwater management all over India. She works on PJWM and has been appreciated by one and all. Now we start with Mihir, and you will change your slides on your own.
Yes, we will do that. Yeah,
okay. So welcome.
Thank you so much, Dheeraj, for those kind words of introduction, and greetings to all of you on World Water Day. We are really happy to be part of a very distinguished panel of speakers. You would have heard very esoteric talks if you've been attending the Congress. And what Uma and I are trying to do today is to sort of bring you back in contact more directly with the lives and livelihoods of some of the poorest, most deprived people of India, and actually we raise issues which would be of concern to those people across the globe. What we want to do today is to speak about what we regard as the most significant, but also most neglected issue on water, which is groundwater. And the key focus of our talk is that somewhere along the line, in our attempt to use groundwater, to manage groundwater, we seem to have forgotten the basics of science. And what we are saying is that if the challenge of sustainable groundwater management in India and across the world is to be adequately addressed, we need to pay closer attention to bringing this science back into water and water policy. Uma, it's over to you. Uma?
Yes, I was on mute. Yeah. So thank you, Dr. Shah, and greetings on the occasion of World Water Day. The theme for this year's World Water Day is groundwater, making invisible visible. And as Dr. Shah rightly pointed out, we are briefly going to talk about this issue, mainly the issue of groundwater pertaining to India. Now, in the next couple of slides, I'm going to stress upon the importance of groundwater. And again, as I said before, it's with respect to the to India. So India is the largest consumer of groundwater in the world. We all know, with the extraction rate of annual groundwater extraction of 245 billion cubic meters, India has exceeded the combined annual groundwater extraction of two countries, USA and China together. India is heavily dependent on groundwater with respect to drinking water supply, because almost 80% of India's rural drinking water supply is sourced from groundwater. It's through the various, the groundwater is used through different wells, bore wells, and also through the springs. It is the most important basis of livelihoods in a predominantly agrarian economy. And one can clearly say that 90% of India's water, which includes both surface as well as groundwater, goes into irrigation, use of irrigation. And 2/3 of it, which means around 65 to 70% of that water, comes from ground. So groundwater is the main driving force. And one can clearly see that in the last 4 decades, around 84% of addition to irrigation has come from groundwater. So when we look at the rural India, you can clearly say that the groundwater is the backbone for drinking water security, as well as for the agriculture and irrigation. Now, we will see about what is the role of groundwater in urban and industrial sector. It is also the key element in urban areas, as it is the main source. So 48% of urban groundwater today in major 71 cities and towns is sourced from groundwater. Now, this is one estimated, this is not the real numbers, because we don't have the actual data. This is one estimate that 48% of groundwater, urban water comes from ground. 56% of metropolitan class 1 and class 2 cities are heavily dependent on groundwater today. Unaccounted groundwater in urban areas exceeds 50% in 28 Indian cities. And most importantly, groundwater abstraction has filled out gaps in public water supply, in the sense that there are many peri-urban sectors which are newly developing, or the fringe areas where the actual water supply from the municipalities have not reached. And all those areas are heavily dependent on tanker water supply. And all those tankers use essentially the groundwater for providing the supply to those communities. As far as industries are concerned, increasingly there is an groundwater is used, although surface water is also used, but increasingly groundwater is used in many of these industries. And the numbers are really not available right now, but one believes that around 35 to 40% of industrial use also is sourced from groundwater. Now, this heavy dependence on surface in rural and urban areas has also led to some crisis. The first and important crisis, or the problem that India faces, is the water tables and the groundwater quality are falling in 60% of India's districts. Now, as you can see in this map shown here, the northwestern India and the peninsular India, you can see some red and amber color districts. All these districts are essentially groundwater overexploited, or the situation of groundwater in those districts is critical. The stage of groundwater development in India is 61% today. At the same time, there are some issues with respect to groundwater quality. Now, nitrate, arsenic, fluoride, Even mercury and uranium are found in groundwater in different parts of India. And they have some catastrophic health consequence in the sense that, as you can see the map below here, there are areas which are groundwater overexploited. And these are also the areas where there are some serious groundwater quality issues. There are some other areas, especially in the eastern part, where groundwater availability is not an issue. But in all those areas, there are serious issues pertaining to groundwater quality like arsenic and iron in groundwater. Now, it is a well-known fact that the Indian peninsular rivers are in the stage of drying up, mainly because of the overexploitation of groundwater. Now, rivers like peninsular rivers like Narmada or even in Godavari, which used to receive groundwater in the form of base flows, are now losing water. So all those gaining rivers are turned into the losing rivers. The springs in Himalayas are also disappearing for a similar reasons. So along with the springs in Himalayas, there are springs in eastern and western Ghats of India, which are slowly drying up because of this major issue or crisis of groundwater overexploitation.
Right. Thanks, Uma. So what our central argument is that what are the roots of this crisis? Where is this crisis coming from? And when we look at that more carefully, we find that for too long, we have not adopted a genuinely transdisciplinary scientific understanding in our formulation of groundwater policy. Without understanding the need for this transdisciplinary approach, I think we will continue to actually aggravate the crisis of groundwater. So what I'm also arguing is that it's not just hydrology or hydrogeology which needs to inform what we do with groundwater. It has to be many other scientific disciplines, which is what we will try and elaborate today. The other key argument we are making is that the fate of India's groundwater is also linked very closely to policies that are outside the groundwater sector, but deeply impact what happens to India's groundwater. So in our presentation, we will also tell you about which are those policies and how those policies need to change if we want to actually be able to preserve and utilize India's groundwater, which is absolutely vital for the future of this country. And the good news is that there is some work already on the ground, which is showing the way forward. The need of the hour is to take that work, that small pioneering work, it has to be taken to scale. And once that is done, I think we would have a very credible, solid solution to India's groundwater problem. So the presentation that we'll make today is essentially divided into three parts. We will begin by listing what are the distinctive features, the differentia specifica of groundwater as a resource based on a transdisciplinary understanding of groundwater. We will then tease out the links of groundwater to policies in sectors outside of groundwater. And finally, we will delineate solutions that would enable us to meet the challenges of sustainable groundwater management, not only in India, but across the globe. So I begin with a brief account of what are these unique features of groundwater as a resource. And what happens when we neglect these features, when we formulate policy, when we act upon groundwater in different parts of the country. So the first most important feature, obviously, is that it is a finite resource. Yes, it is renewable, but that renewability of groundwater has definite limits. And there are many situations which we will just illustrate to you, where in certain kinds of aquifers, we have almost totally exhausted groundwater, which took thousands of years to accumulate below the ground. So without paying close attention to finitude, we will not be able to formulate proper groundwater policies in India. The second element of groundwater, again, something which every school student is actually taught in their classes, that there is a water cycle and every element in that water cycle is connected to the other. Neglecting these interconnections of different elements of the water cycle with each other have definitely led to to an aggravation of groundwater crisis in India, and we will try and explain that in some detail. Third feature is the diversity. The diversity in the occurrence of groundwater and the nature of aquifers found across the length and breadth of the country, the variations in the transmission and storage characteristics of these aquifers are very important elements which we have neglected so far. But taking them into account, we can certainly formulate meaningful policies to address the problem of groundwater. And finally, we must recognize that this is a common pool resource. It's a common pool resource which is also fugitive in nature, which means essentially that establishing exclusive property rights is extremely hard and also extremely hard to enforce these rights on the ground. So all of these four features put together make us understand what is so difficult about the management of groundwater. And now Uma will take us through a description of the diversity of this resource across the length and breadth of India. Uma.
Yeah. So India is a lithodiverse country. Almost 80 to 85% of rock types that are found globally are found in India. And as you can see in this map does not depict the different rock types, but here I'm presenting something that is what we call as hydrogeological typologies or hydrogeological formations. It is based on the broad geology that is found across the country. So each color depicts a particular hydrogeological system here. For example, the pink part, which forms the part of peninsular and eastern India, is the crystalline hard rock system. It occupies almost 33% of India's landmass, which is followed by the alluvial system, which is unconsolidated system, which is found in the Ganga basin. This is it forms around 28% of the total landmass, followed by the volcanic or the what we call as a Deccan volcanic province. This is around 60% of the total area, which is followed by the sedimentary systems, which is around 20%, and the blue color indicates the hard and soft sedimentary systems that are actually that are the good aquifer systems that are found in the country. And lastly, as you can see, the red dots across the country, these are the lateritic systems, and these are the areas where you can find there is a possibility of finding good springs. And so one can say that these are the springscapes area of the country. Now, we have to connect these hydrogeological systems with the aquifers. And when we look at the aquifers and their groundwater possibilities, one can see that in the Himalayan mountain systems, the dependency is essentially on the springs. So the communities are dependent on spring water. And these springs are underlain by a diverse system of local and leaky aquifers that are controlled by fractures. Then we have this huge alluvial systems. Now, these are the regional systems where you can find from tens and hundreds of villages, which are underlain by the same aquifer system. These are, as I said, these are regional systems. And there is a possibility of tapping multiple aquifers in alluvial areas. You have plentiful groundwater, but some of these systems are most exploited groundwater systems, most exploited aquifer systems in the world. There are also some serious contamination issues, like you may have issues pertaining to finding excessive amount of arsenic, iron, fluoride in these aquifers. Then you have consolidated sedimentary systems, which are local to regional aquifers, and that are governed by the lithological and structural factors. Then you have volcanic systems, which are layered and heterogeneous aquifers, in the sense that you have varied transmissivity and storativity values. And most of the systems are tapped by the aquifers are tapped, the sources are large diameter dug wells or bore wells. Lastly, you have crystalline systems, which are hyperlocal to regional, but these are relatively thin systems which are formed because of weathering and fracturing of igneous and metamorphic rocks. Now, these are complex hydraulic, there is a complex hydraulic relationship between the shallow and deeper aquifers. And there also is an element of some contaminants that are found in this area, like fluoride. So over to you.
Yeah, thank you, Uma, for that, because that really gives us, in a very synoptic view, what we are dealing with when we talk of the aquifers of India. And when we examine groundwater use, the actual groundwater use based on these aquifers, then we find that this use does not recognize the common pool resource character of groundwater or its diversity. So what we have is a situation of indiscriminate and deep drilling for groundwater in a country with more than 2/3 hard rock aquifers, and this obviously creates grave problems because we have a common pool resource which is shared across users being subject to competitive extraction by millions of small individual users. So individuals are competing with each other to access common pool resources, and that is plummeting that resource into a state of destruction. Who are most of these people? Around 700 million of them are small and marginal farmers who are tilling less than 5 acres of land. As they go competitively deeper and deeper below the ground, they jeopardize the access of their aquifer neighbors who are, so to speak, joined at the hip with them. Not only do they, of course, deprive their neighbors, they also destroy the very resource on which their own lives and livelihoods depend. So this is really the dilemma that the country faces. We cannot continue this unbridled competitive extraction of groundwater to deeper and deeper depths. But it is also not possible to police 50 million groundwater structures. That's the latest estimate. Most of us believe that is actually an underestimate of the actual number of groundwater structures that have been created across the country. The problem is you cannot be employing a licensing system or a system by which inspectors go and see how much groundwater people are using, because that would only proliferate a huge bureaucracy and create massive corruption across the country. So the question then, which we want to pose to you today, is what is the way forward? So, as I said, there is some good news. The good news is that India has embarked on what may be called the largest aquifer mapping exercise in human history. It's at a scale which has never been attempted before. And by scale, I mean both the scale of coverage, the millions of hectares of land that governments across the country are trying to cover through this aquifer mapping program, but it also refers to the scale of manageability, which means it is the scale at which information can be provided to primary stakeholders of groundwater so that they can use this information in a way that enables them to more sustainably and equitably share this common pool resource with each other. And there is an example of 1 million farmers in several states of the country that are mentioned in this slide who have come together to actually do this work of participatory groundwater management, which is, we believe, the way forward for the country. What needs to be done, therefore, is to shift the focus from the supply side, from the endless extraction of groundwater towards demand side management, so that we go into issues like crop water budgeting and, of course, ally that with a groundwater recharge program. So what this would involve is actually the principle of subsidiarity in the first instance, which means the principle of subsidiarity refers to the principle of finding solutions closest to where the problems are and involving the people who are closest to where the problem are in finding the solution to that problem. So what do we have to do? We have to protect the recharge zones of groundwater. We have to try and sequence well use so that the water that is available in number of wells across the village is used in a manner that provides for their sustainable water use across the season. Pump capacity regulation. We cannot have pumps being used beyond a certain capacity because they're exhausting the groundwater found in the aquifer. But who will do this regulation? We cannot have bureaucracy coming from the outside. Self-regulation has proved to be the most effective way of doing this, along with distance and depth norms, so that tube wells are not drilled very close to each other. They are not drilled beyond a certain depth. And finally, crop water budgeting, which is essentially aligning the cropping pattern to the local agroecologies, to the local availability of groundwater. Once people are given this kind of information, evidence shows that they come together to manage their groundwater in a sustainable and equitable manner. Now, while we can say that it is the primary stakeholders of groundwater which have the main responsibility in sustainably managing groundwater, the fact is that unless the overall policy environment is to change, as I said, there are policies in different sectors which impact the fate of India's groundwater. Most importantly, British common law of the 19th century, which provides unlimited access to landowners to water below their land, that is still in operation. I had the rare honor and privilege of chairing a committee set up by the government of India to draft something different from the British common law, which could replace British common law. And we called it the Model Groundwater Sustainable Management Bill of 2017. And I've just quoted a few lines from that bill to give you an idea of the direction in which the legal structure is sought to be changed. And the bill says groundwater in its natural state is a common pool resource, and the Supreme Court of India has applied the public trust doctrine to groundwater, which means that governments at the local level must be seen as acting as trustees of the public interest, so that nobody should use groundwater in such a way that it adversely impacts the realization of any other person's fundamental right to safe water for life. And we have tried to use the principle of reasonable restrictions on unreasonable use, which is actually something which is part of water law across the globe. And that is the kind of law India needs if we have to support the actions of primary stakeholders on the ground, of the farmers who are trying to be economical and sharing in their use of this common pool resource. But without the legal backing, it's going to be very difficult. Similarly, we have to change the structure of incentives. Why is it that people are growing water-intensive crops like rice and wheat? Rice, wheat, and sugarcane today take up 80% of India's water use. But these are the crops farmers are growing because the government of India continues to procure rice and wheat in order to fulfill the needs of food security. But if you continue to do that, then there is an economic incentive created for farmers to continue to grow rice and wheat, even in regions where water is short. And what we are arguing very strongly is that in regions, especially where there is a shortage of water, where agroecologically it may make much greater sense to grow millets, or what are called nutri-cereals today, local oil seeds and pulses, crops which are both nutritionally superior to rice and wheat, but also use far less water than rice and wheat do. If we have a good mixing and matching of these crops with the agroecology of different regions in India, then I think we would go a long way to addressing the crisis of groundwater. And the question I'm normally asked is that when you make this proposal, what are we going to do with these things? Who is going to eat them? Well, I think we have a major crisis of malnutrition and diabetes in India. And the best way of addressing that crisis is to make these nutritionally superior and less water consuming crops part of what are the largest preschool and school nutrition programs in the world, which India is running. And if we do that, we are tackling multiple problems in one stroke, because we will tackle the problem of nutrition. We'll also get a handle on our groundwater overexploitation. Another element of policy change that is required is to do with the kind of farming that India has done, the rest of the world has done since the days of the Green Revolution. This kind of chemical input intensive farming is highly water consuming. And I have placed before you a long quote from the Food and Agricultural Organization, which in 2017 has strongly committed itself towards agroecological farming, because for multiple reasons which are stated in this slide, it is far better to move towards an agriculture which tries to leverage the power of nature, and in doing so actually makes a huge contribution towards conserving the groundwater that we are endlessly depleting in India. And most recently, most powerfully, the Honorable Prime Minister of India has made a strong case for India to move towards what he calls natural farming, which is essentially farming based on the agroecology of each region. So these are the kinds of changes in farm policy which would be required. But there are major changes that are required in the governance of water and groundwater in India. Because what has happened in our water management is that we have divided water into different kinds of silos. This is sometimes in the literature called hydroschizophrenia. So what do we have? We have a different department dealing with irrigation and another one dealing with drinking water. What this does is that when there is an aquifer which is providing drinking water to people in a village, if the same aquifer is being used for irrigating water intensive crops, very soon we find that the source of drinking water is dried up, and people, although they are being, some of the rich farmers are being able to irrigate water intensive crops, most of the people in that settlement are no longer able to access drinking water from that aquifer. Something similar has happened with surface water and groundwater. So we divide the departments dealing with surface water and groundwater, keep them separate. They don't talk to each other. The result is that what we mentioned earlier, many of India's rivers are drying up, because once you over extract groundwater in the catchment areas of our rivers, the base flows of groundwater which feed rivers in the post-monsoon period are dried up. And so not only are aquifers getting depleted, but the river systems are also being destroyed because of this hydroschizophrenia, which we have made a part of water governance in India. It also, of course, leads to poor water quality, because water and wastewater are also not treated together, which raises serious health concerns. So in several reports in the recent draft of the new national water policy, which I was chairing the committee which was supposed to draft that national water policy, we have strongly advocated that this hydroschizophrenia must be ended. And without doing that, I do not think we will be able to restore our water tables, our water quality, and groundwater crisis will remain where it is in India. Another element of the kind of governance reforms that we need, Uma, you can go to the next slide, please. Yeah. What we need is what we have been talking about, a transdisciplinary approach to water governance. You look at any water resource department in India, you will only have irrigation engineers, civil engineers, hydrogeologists. You will not have people from social sciences and management. If you do not have professionals from these disciplines, how will you ensure participatory groundwater management? How will you ensure that the conflicts that are arising around groundwater can be adequately resolved? If we want to do crop water budgeting, which is absolutely essential to tackle the demand side of groundwater and to improve water use efficiency, we need to have agronomists. In every water resource department at the center and the states in India, we need to have people who have a proficiency in seeing how cropping patterns can be tweaked in line with local agroecologies. We need ecological economists who will be able to accurately estimate the value of the ecosystem services that are being provided by different elements in the water cycle. Without doing that, we will continue to overexploit groundwater and not get into a new framework of understanding how groundwater can both be preserved and serve the lives and livelihoods of the people of India. And of course, river ecology, which is absolutely important to understand how rivers can be rejuvenated, what are the links between river systems and the aquifers that lie within those river systems. Without having river ecologists on board, we will not be able to solve the groundwater problem in India. And in the end, I would say the most important change that we need to make is that we require a people's movement around water. It's all right to have all the professionals. It's all right to reform how government functions. But without a novel architecture of partnerships with all primary stakeholders, from civil society, academia, farmers, elected representatives, industry, etc., without utilizing the knowledge and experience of the people of India, who have a long history and a long wisdom in having managed these resources sustainably, without all of these people having a place, an enduring place around the table of decision making and policy making in India, we will not be able to resolve the groundwater crisis. We will not be able to revive the rivers of India. Thank you very much. Uma, you can close the presentation.
Oh. Thank you, Mayor, and thank you, Uma. Excellent talk. And there is something which everybody should realize, that there is a crisis, and we are in the really middle of the crisis. As a teacher, being a teacher, my solution is two. One is making people aware, teach them, because unless there is an education, people will not understand the importance of this thing. So you have to change the attitude of the people and the awareness of the people, and the political awareness of the people, and the administrators and the district magistrate type of level of people. They should understand the situation. Unless they understand it, nothing will happen. You keep on making all the stories and nothing will happen unless people participation is there. Thank you very much. Okay, wonderful. Sure. One. Okay, the live है, let it be. कैसे होगा भाई? Okay, at the end of the successful third and the last day of virtual 36 IGC, I want to make some concluding remarks about the history of 36 IGC, especially for the younger generation and the posterity who will evaluate us in due course of time. A concise story needs to be retold. To bring IGC to India after hosting it for the last time in 1965 was the brainchild of only one single individual, Ashok Kumar Singhvi, then a young geoscientist at the PRL, who tried to make a bid in 2004 at the Florence congregation with support from the NGRI. He did not succeed then, but without losing hope, he again made a bid in 2008 at the Oslo IGC. It was the foregone conclusion in the Oslo that IGC will go to African continent, where IGC was never held. Finally, in 2012, IUGS National Committee and the president of INSA invited GSI, which in turn meant the Ministry of Mines, to join hands along with the Ministry of Earth Sciences to bid and projecting the GSI, the biggest geologist employer of the country, as the lead organization. The bid document was introduced before the IGC. Bid document was introduced by the chair of the IUGS National Committee, followed by an argumentative presentation before the IUGS Executive Committee by Shailesh Nayak, the then Secretary of the Ministry of Earth Sciences, and that was followed by a spirited defense by Ashok Singhvi before the general body of IUGS, where secret ballots were drawn. The bid was won with a thumping majority in a direct contest with Canada. It must be remembered that the bid team included stalwarts like Vishwapat Tripathi, S.K. Srivastava, A. Sundaramurthy, D.K. Bansal, R.K. Chadha, J. Jaggi, R. Ravin Mohan, S. Chinoy, T. Ramasamy, Naresh Kumar, H.S.M. Prakash, and representatives of the ONGC. Together, they boosted the morale of the Indian contingent. Vishwapad Tripathi also announced the assured Government of India's financial commitment and support for the proposed Congress. The date was August 9, 2012, and it was my 70th birthday. Winning the bid was the ultimate gift I could have expected on my birthday. It was, however, I was seriously apprehensive if I will live to that date and attend the Congress in 2020. I did survive. The preparation for the Congress started with right earnest, and in November 2012, over 100 responsible and experienced Indian geoscientists and administrators of the country assembled at the Indian National Science Academy and prepared a detailed blueprint for the Congress. Something happened at that juncture, and I will not discuss it here, but the thread of coordination was snapped and a new culture took over, another with altogether different aims and objectives. An autonomous society was registered with the registrar of the societies for smooth management. Shailesh Naik was appointed the president of the society, but unfortunately, no scientist was given the task of the secretary general. God had ordained differently, and the society was completely wrapped with red tape. Then the president resigned to also the chair of the Science Programming Committee, the most crucial positions in the IGC organization. A new president was selected after long dilly-dally. In spite of all the hurdles, a substantial number of GSI, MOEs, and university scientists joined hands, worked hard, cutting through all the obstacles, and made excellent executable plans for the Congress and the field excursions in different parts of the country. Finances was never a problem, as Cabinet had provided substantial sum with the two partners ministries, MOM and MOEs. Intellectual inputs were provided by the INSA and its fellows, who looked after all crucial activities related to the Congress. We all know why we failed to hold 36th IGC at the appointed time. It was a trying time after the date it was postponed in August, hoping that viral infection will subside. It is everybody's knowledge what happened after that. It was decided to refund registration fees to the delegates, and everybody started looking dejectedly to the official announcement of cancellation of the event. Doggedness of some of us prevailed over those who had resigned to the fate. A new Secretary General with dogged support of a few individuals broke through the remorseful environment and accomplished the task of successful organization of an attenuated IGC on a virtual platform. I take this opportunity to show our appreciation to the role played by Shailesh Naik, Ashok Singhvi, the early crusaders. The officials like N.K. Singh, B.P. Dimri, P.R. Golani, Rasik Ravindra, and Ranjit Rath, who temporarily occupied the positions of President and Secretary General at different times. They contributed immensely in giving a stable shape to the IGC event until it was almost abandoned. I wish to record appreciation for the major contributions made by the Scientific Programming Committee members chaired by Talat Ahmed, P.P. Chakravarti, Field Trip Advisory Committee chaired by Somnath Dasgupta and N.R. Ramesh, Legacy Committee chaired by Fariduddin, Geo's Support Committee looked after by R. Shankar, and Volunteer Committee managed by E.R. Ramanathan. All these committees were very meticulously supported by experienced conveners like Snigdha Ghatak, Shaibal Ghosh, Devashish Raut, S.P. Shukla, and S.N. Bhagat. Each committee was supported by a galaxy of senior professors from the universities and officers of the GSI. All of them are entitled to receive a mention in this list. In the last phase of activity, the IGC Secretariat was meticulously managed by Joyce Bagchi, Devashish Raut, Sangeeta Gupta, Manish Kumar, S.N. Bhagat, and Palak Kapoor. The administrative staff, Krishna Mohan, Vinaypal, Himanshu, and workers like Surjit, Parvesh, Altaf, Madhavi, Naresh, Jitendra, Mahesh, and Falguni were the source of comfort to all of us who spent hours in the small cabin office. I express my personal appreciation for the unqualified support received from Alok Tandon, the Secretary Ministry of Mines, and Ravi Chandran, Second Secretary Ministry of Earth Sciences, and Chandrima Shah, INSA President, and all other previous INSA Presidents who gave me free hand in managing the academy role in 36 IGC. On a personal note, I confess that it was my good fortune to interact and work with an efficient, accommodating, and friendly secretary at the Ministry of Mines, and helpful economic advisor Shakil Ahmed, and a wonderful director technical Pradeep Singh. I am also happy to express my pleasure of working with new Secretary General Venkateshwara Rao Sahab for his highly cooperative and proactive attitude. Co-President Janardhan Prasad ji also provided advice to young team members wherever required. Vishwapriya Khori, whom I had taught in the university days, did a remarkable job in conducting the inauguration program with innate professionalism. Kudos to Vishwapriya. All concerned union ministers participated through recorded videos, and we are grateful to all of them for their unqualified support and words of encouragement. 2 commemorative stamps and several publications were also released. I am thankful to the Geological Society of India, and in particular N. Rajendran and Ed Saukar for helping us in supervising and producing the abstract ebook. I must thank Arun Chawla, DG Fiki, and his team consisting of Balwinder Singh, Vinay Gupta, Vivek Mishra, Saurabh Pandey for very efficiently managing the entire show with permanent smiles on their faces. I also thank Sneha Pandey for creating a beautiful website and bearing with my unending tantrums. I express my thanks to all the scientists who participated in the technical sessions as speakers and session chairs like Owen Bhargo, Ashok Tangvi, Pradeep Srivastava, and Talat Ahmed. My special thanks goes to Ranjit Rath for convincing the IUGS president the necessity of holding the virtual IGC. I express my personal appreciation to John Luden, the president of IUGS, and Jane Hussey for providing a protection shield during a very critical phase. Some of you must be feeling concerned. Why did I not say anything about an important persona in the IGC crowd? I reserved a very, very big, resounding thank you for Rajendra Singh Garkhal, the president of 36 IGC and DDDSI, for leading the team in a way it should have been, by giving total free hand to all of us and allowing us to mold the Congress the way we wanted it to be. At the Samapan function, I conclude with a big clap to the entire team of Garkhal. Can you see this virtual workforce behind the 36 IGC? I tried to assemble all those pictures at one place and hope you'll enjoy this. And thank you.